Dr. K. Sakthimurugan from Department of ECE, PSN College of Engineering Technology. Today I am going to discuss about the design of arithmetic circuits. So here the generic digital processor. So this is nothing but a process consists of memory element and the data path and input output and control unit. So the input output nothing but they are giving input and proportionally are getting output, and data path is nothing but a processing unit. It consists of arithmetic circuits, adder, subtractor and memory full adder and mux, demax, etc. Memory it consists of latches, lot of latches will be there, SR flip-flop, D flip-flop. So it will be store the informations, and control unit is nothing but it will control the input as well as output as well as the output circuits. Okay. Next, building block for the digital architecture. So here there is a given as it is discussed: arithmetic unit, bits like data path, adder, multiplier, shifter and converter, etc. Memory, RAM, ROM, buffers and shift registers. Control unit consists of a finite state machine. Finite state machine consists of there is a two. One is a Mealy machine, another one is a Moore machine. Programming logic array, random logic, counters, interconnect nothing but a switches, arbiters and buses. It will connect the one block to another when you are using a system on chip. An arithmetic block, building block, speed and power of arithmetic components often dominates the overall system performance. That is nothing but why we are considering speed and the power of arithmetic components is nothing but the speed is the main factor when you are going to analyze about the arithmetic building block. The operation will be very fast. Then only the when you are giving input, the processing time will be reduces, and the power of arithmetic components. When your power consumption is main factor when going to analyze about the system on chip. So here the speed and power is the two criteria when you are going to analyze the arithmetic building block. So that dominates the overall system performance for each module. Multiple topologies and way design exists. Each of them has own advantage. So the speed and power have there is a different models. It will discuss about the different topic and multiple topologies also there. So global picture is a crucial importance. Designer focus their attention on gates or transistors that have largest impact on their whole function. Non-critical components can be developed routinely. So typically two optimization process. One is a logical optimization, another one is a circuit optimization process. So logical optimization, we are familiar about that. When you are using a Boolean expression, we have to optimize the process. And in case of circuit optimization, when we are minimizing the circuit by using a pass transistor or maybe a transmission gain based on the application of our requirements, whether we have to connect a logical optimization or maybe a circuit optimization. So if logical optimization means you have to simplify using a Boolean expression. In circuit optimization means you have to use a circuit, find out the circuits, and that particular circuit, the particular device will be implemented in a particular circuit. We have to minimize the power reduction. So that is about the two optimization process when you are discussing about the arithmetic building block. So next, build bit sliced design. So here there is a data in, and there is a register, and there is a adder, and there is a shifter, and there is a multiplexer. So here data in is nothing but it will give the input data, and whatever data feed will be stored in the register, and after that there is a adder circuit, that means nothing but a processing unit. And if you want to shift the data by using a shifter, and multiplexer nothing but selection. Based on the selection, whether maybe a addition operation or maybe subtraction operation, whatever performance we have to do by using a multiplexer selection. So this is the data in and data out. So we are giving a data input here and register, and after that adder. So instead of adder we have to give some other circuit, comparator circuit, or some other process unit maybe we have to use. So this is about the bit slide data bus. So this is a control unit. This control unit is nothing but control the input data. So as well as the processing data. So since there is some operation has performed on each bit of a data word, data path can be consist of number of bit slices equal to word length. Each operating on a single bit is called bit sliced term. So next adders. So it is the main part in this arithmetic building block. So here first one is the full adder. Full adder consists of there is a 3 inputs and 2 outputs. So first one is A, another one is B. Here there is nothing but a carry in. So here there is a sum and C out. So here 3 inputs and we are getting 2 outputs, sum and C out. So here there is a tabulation shows that there is a input as well as output and carry status given in the truth table, or the tabulation shows that. So here there is it is a 3 input means how many possible combinations? So 8 possible combinations. First one is 00, 000, 001, 010, 11, 100, 101, 110 and 1111. So here our concept is generate. So carry generate nothing but A into B, propagate nothing but A XOR B, delete nothing but A bar, B bar. So now here the 3 inputs are 0, that means A input and B, and carry input is equal to 0, sum is equal to 0. So what A XOR B? So nothing but it will be 0, A XOR B XOR C. So totally it will be 0, and carry status also 0, A not B, and the status will be delete operation. So delete operation nothing but, so nothing is there, so it is nothing but delete operation. Delete means A bar, B bar. So there is both will be A bar, here it is A bar and B bar. So we will consider as a delete operation. And next input 0, 0, 1. Here A and B both will be 0 and C is equal to 1. What about the sum? Sum is equal to 1. So what happened? What about the carry output? Nothing but delete. So here nothing but A and B both will be 0. So definitely we have to say delete operation, delete status. And third one is 0, 1, 0. So we are familiar about that. When you say different input, output will be 1 in case of XOR. So here A is equal to 0, here it is B is equal to 1, and carry input is equal to 0, 1. So sum will be definitely 1, and here the propagate will be A XOR B. When you propagate A XOR B, the output will be so here it will be propagation operation. Now next third one 0, 1, 1. So it will be sum will be 0 and carry will be 1. So here also propagation operation, and 1, 0, 0, here will be 1 and here will be 0, here also propagate, and 1, 0, 1. So here A is equal to 1, B is equal to 0 and C is equal to carry input is equal to 1. So definitely we know that 1 XOR 1 is equal to 1, 1 XOR 1 is equal to 0. So definitely this sum is equal to 0, carry will be is equal to 1. So it is nothing but propagate option. So next A is equal to 1, B is equal to 1 and carry is equal to 0. So sum is equal to 0, carry is equal to 1 because A into B. And final A is equal to 1, B is equal to 1, C is equal to 1. So if you multiply, if you XOR that, definitely sum is equal to, what happens here, it is here it is 1, carry is equal to 1 and sum is equal to 1. So what happens, 1 XOR 1 is equal to 0, 0 XOR 1 is equal to 1. So sum is equal to 1 and carry output is equal to 1. So because we are multiplying A into B. So that is why here it is generate, and previous also A into B. Generate is equal to A into B. So that is why A into B is nothing but 1. So that is why here it is nothing but a generate option. So this is about the full adder. Generally used for the full adder is used for addition process. So 3 input and 2 outputs. So next, binary adder. So here as it is same, here it is the equation is given. Screen A and B are 3 inputs and 2 outputs. Sum is equal to, equation is given A XOR B XOR Ci. So we have to return this expansion in A XOR B XOR C, nothing but A bar A, B bar C bar, A bar B C bar, A bar B bar C and A B C. So and in case of carry output, you have to multiply AB, BCI and ACI. So this is about the equations for binary adder or full adder. Okay. Next, ripple carry adder. So ripple carry adder consists of 4 full adders connected in seriously. So here there is a first full adder, A full adder 1, full adder 2, full adder 3, full adder 4. So input is A0, B0, A1, B1, A2, B2, A3, B3 and input is Ci of 0. So the carry output will be input of a next full adder, and this carry output of this full adder is connected to a next full adder, and carry output of this full adder is connected to a next full adder. Finally we get the C03. So here the drawback of ripple carry adder is nothing but when the carry depends upon the previous adder. So what happens, definitely the carry will be delayed. So when you are delaying, when the carry is delayed, the final carry out will be taking large time. So what happens, nothing but there is a delay in process. That is why here it is given as worst case delay linear with number of bits TD on. So D add nothing but n minus 1 T carry plus T sum. So that is why it is called a ripple carry adder. So this here the Cout will be getting large time. So what happens, so there is a delay in this process. So you have to minimize these operations, definitely the carry will be improved. So that is why it is called as ripple carry adder. So next, complementary static CMOS full adder. So here there is a full adder consists of, this is nothing but carry generate. Here it is nothing but a propagate or Cout. This is nothing but a Cout. So sorry, this is the Cout value, this is the sum value. So we have the equation, we already studied about the equations previous slides. So nothing but the equations of A XOR B XOR C. So you have to convert A XOR B XOR C and AB, BC, CB for the carry. So this is the AB, BC for the carry equation converted into the complementary complementary static CMOS full adder, and A XOR B XOR C is converted into CMOS full adder. CMOS is consists of both PMOS circuit as well as NMOS circuits. So here there is a inverter connected, so the output will be inverted and connected to the Cout. Same as it is here also, there is a inverter circuit connected, and this inverter circuit will be connected to the output of a sum. So here total around 28 transistors will be connected in this complementary static CMOS full adder. So next, the large PMOS stacks are present in both carry and sum generation circuits. So in case of this complementary static CMOS consists of PMOS as well as NMOS, and PMOS stack also presented. So what happens when you are connecting large PMOS connected in this circuit, means definitely the speed will be reduces and delay will be increased. That is the main concept. And intrinsic load capacitance C0 signal is large and consists of 8 capacitance components. So we already studied about that. Parasitic capacitance are large in case of mass per circuit. So this PMOS as well as NMOS both will create then a lot of capacitance, parasitic capacitance and diffusion capacitance. So it is a main factor for dissipating large power dissipation. There is one more inverter delay for carry and sum. So we have to convert this sum into when getting a sum, that will be converted into a inverter, connected to a inverter circuit. So that particular inverter will create a delay. So the Cout and as well as sum both having both will be converted to inverter circuit. So it will give an additional delay. That is why there is one more inverter delay for carry and sum. So worst and last load capacitance is large. Then note that the critical signal is closer to the output node. So this static CMOS having such a drawback for the delay process. And express sum and carry as a function. So this we discussed previously. We have generate is equal to AB, generate, propagate is equal to AXR B, and delete A bar B bar. So here C0 into generate propagate is equal to generate plus propagate into Ci. So sum of generate into propagate into PXR of Ci. So this can be expressed in S C0 based on the T and B. So this is the expression when you are carry out this sum and carry functions in the full adder circuits. Okay. Next, transmission gate. So what is a transmission gate? So transmission gate is nothing but, so when you are giving, when the circuit consists of both PMOS and NMOS combined together, so it is called as the transmission gate. So here the transmission gate XR. So by using a transmission gate, we are converted into XR gate. So now, transmission gate is nothing but the output. When you are giving input to a transmission gate, the output will be a strong signal. So that is why whenever the strong signal is required, we are preparing the transmission gate. So here there is a circuit called as the inverter. When you are giving input to a inverter circuits, and output will be kind of a transmission gate. And what happens when there is a input signal, and when you are B is equal to 1, what happens? This M2 will be getting supplied. If A is equal to 0 means the M will be activated. If A is equal to 1 means M2 will be activated. Assume that when A is equal to 0, what happens? M2 will be activated. So what happens? There is an output at the F. This F will be counted at the output of a. So provided there is a input signal when B is equal to 1. So what happens? B is equal to 1 means here it is. B is equal to 1 means it will not be operated. Here it will be B bar is equal to 0. So this is PMOS as well as NMOS combination. PMOS and NMOS combination together we call as the transmission gate. So now B is equal to 1 means here there is PMOS will be off, NMOS also off. So the whatever give the input will be reached at this point. So now when B is equal to 0 and B is equal to 0 means here it will be B bar is equal to 1. So B is equal to 0 means what happens? Here it will be 0. So when A is equal to 0, what happens? So it will be A is equal to 1 means what happens? This B bar. So B is equal to 0, B bar will be 1. This 1 will be coming to the output and it will be connected to the F input. And finally we get the input. So when B is equal to 1, M1 and M2 inverter will be on, and M3 and M4 will be off. M3 and M4 will be off. So F is equal to A dash B. When B is equal to 0, M1 and M2 will be off, and is equal to 0 means here will be 0. What happens? Here will be 1. So what happens? So M1 and M2 will be off. M3, M4 will be a transmission gate. So F is equal to A B bar. So now transmission gate full adder. So it consists of, there is a adder consists of 3 inputs and 2 output, sum and carry. So this is the input we called as A input. So it will be kind of the input inverter circuits, and this is nothing but A and B when you are connecting through a transmission gate, and it will be kind of a sum generation circuit, and this will be kind of a carry generation circuits. So now this is the A input and this is nothing but a B input. through the equations. So what happens here, there is a set of time, and so B is propagate is equal to A XOR of B, C naught is equal to generate into propagate is equal to G plus P into Ci, S is equal to generate comma B is equal to P XOR of Ci. So transmission gate full order consists of, there is two category two outputs, one is sum generation, another one is carry generations. So input nothing but A and B, and this is nothing but a carry inputs. So these are all, these three connected to the sum generation circuit, and we will get the sum generation, and these three are connected as well as in the carry generation circuit we will get the carry outputs. So this based on the transmission gate we are getting sum and the carry output. So next, Manchester carry adder. So here there is an input called as propagate, and there is a C, and there is a generate, and there is a C out. Okay. So here generate, G is equal to AB, propagate is equal to A XOR of B, delete A bar C bar. So now Ci is equal to connected to a transition gate, and propagate symbol Pi and Pi bar, and this will be connected to a C naught. So now generate is equal to G is equal to A into B, propagate is equal to A XOR of B, delete is equal to A bar C bar. Now what happens? So the Gi bar is equal to connected to a inverters in this PMOS circuits, and DA connected to the NMOS circuits. So now what happens here, when we are giving a Ci is equal to in Ci is the input, when Pi is equal to 0, what happens? This will be CMOS will be when Pi is equal to Bi bar is equal to 0, what happens? Here will be PMOS will be active, this NMOS will be active, so Ci will be connected to the circuits. If Di is equal to 1, what happens? This one will be connected to this C naught. Otherwise, if Gi and Di are off state, what happens? Whatever input at the Ci will be transferred to the C naught. So here same as it is Ci bar and Pi, and there is a PMOS circuits and generate NMOS circuit, and there is a clocked inputs. Here based on the clocked input we are connected to the NMOS circuit. Suppose the clocked input is 1, what happens? This will be connected to the Gi, provided Gi and here also is equal to 0 or 1. See this, here this 0 means this VDD will be connected. So pi is equal to 1 means this will be connected, and J is equal to 1 means it will be active. Whatever input in the ground, that means 0 will be connected to the C naught. Otherwise C bar will be transferred to the C naught. So this is about the Manchester carry chain. So based on the generate simple formula, and based on the propagate formula and delete, we have to work out this Manchester chain. Here there is a same tabulation given for the full adder, when as it is previously discussed about this same concept. Here ABC is equal to 0, so there is a delete status, and any one of the is 1, also there is a steady status. And here because the concept is A bar B bar, here it is 0, here it is B, so both will be 0 0, that is by steady status. Here also 0 0, both will be steady status. Here 0 1, 0 1 means it is A XOR B, that is nothing but XOR state. There is a state will be when it is different input, output will be 1, that is why it is propagate. And here also 0 1, that is why here it is propagate, and here it is 1 0, there is a propagate, and 1 0 here also can propagate. Now both will be high, so that means generates. So A into B, I am here A into B, nothing but generate. So next, Manchester carry chain. So already we discussed about the single block we discussed. Here there is a multiple blocks are ordered. Here there is a one set, and there is another set, this is another set, and this is another set. The concept is same. When you are giving a say input based on the pi or clock pulse, what happens? If it is enabled means the input this VSS will be connected to the G0, and suppose VS is equal to 1 means it will be connected, but here it will be, what happens it is, and PMOS will be off state. So So like that, it will also there is a chain. So now, so we will get this C0 output, and same as it is here, it is another pi. Suppose C0 pi is equal to 1 means what happens? This will be on. So there is a BDD will be kind of a supply. So we will get CI output is nothing but I input. So based on the input, or based on the clock input, or maybe a pi signal, whether the carry will be generated or carry will be 0. So that is about this is nothing but a Manchester carry chain. So this is the one set of block, this is another set of block, this is another set, this is another set. So 4 blocks are there. Based on the blocks, 4 blocks, so the carry will be generated. Finally we are getting C bar 3. So next, this delay for the Manchester carry chain can be modeled similar to a linearized RC network as in the transmission gate. So when you are connecting the carry chain, what happens? The MOSFET generally have a parasitic capacitance. There is a RC delay, resistance and capacitance delay. So due to the resistance and capacitance delay, what happens? Finally, the delay will be increases. So this means that propagation delay is quadratic in the number of bits, but does not imply that delay will be larger than the ripple carry adder. It might be necessary for the insert signal buffering inverters. So still ripple carry adder typically one good for a small word length. It is generally for the less than 8 per 16 birds. We need faster adders for computers and multimedia application with a word length of 32 to 128 bits. So this is about the Manchester carry chain. Here the delay for Manchester carry can be modeled similar to a linear RC networks. So RC delay model. So RC delay model means each block having a resistance and capacitance. So suppose n blocks are there, means n number of RC delay network will be there. So this is created based on the parasitic capacitance as well as diffusion capacitance in the MOSFET circuits. So we have to analyze this RC network, then only we have to get the final output. So by using this we have to find out all the propagation delay also there. So next, carry bypass adder. So what is carry bypass adder? So here nothing but there is a 4 bill of full adders. The input will be P0, G0, propagation 0, generate 0, propagation 1, G1, generate 1, propagate 2, generate 2, and B3, G3. So when you are giving, this is nothing but a ripple carry adder. So this is nothing but this full adder depends upon the previous full adder. This carry depends upon the previous ripple adder. Like that, the carry will be delaying. That is why we call it the ripple carry adder. But the topic is nothing but carry bypass adder. So when the signals are propagate impulse inputs P0, P1, P2, P3 will be 1. What happens? The input will be directly kind of the multiplexer. When what happens? So it will be selected. When it is 0 means it will be selected 3 full adders. When it is 1 means directly connected to the multiplexer. Finally we will get the C03. So now the carry bypass adder is very advantageous when you are using the adder circuits, because when you are A input, B input, C input and D input both will be 0 or both will be 0, 1, 1, 1, 1. What happens? There is no need of the carry operations. It will be directly connected to outputs. So that is why the idea is nothing but if propagation 0, when there is a different input signal, there is a by using XOR gate, there is an output will be there. Where XOR gate operation, when it is a different input, output will be 1, remaining state output will be 0. That is why idea is given P0, P1 and P2, P3 is equal to 1, C0, 3 is equal to C0. Else delete or generation option. So this is nothing but a carry bypass adder, also called carry skip adder. Both will be same. Here there is nothing but a carry bypass adder circuits. So now here there is a 4 bit, so nothing but a 16 bit. So here there is a block controlled by 4 bit, and this block controlled by another 4 bit, this block controlled by another 4 bit, and this block controlled by another 4 bit. Now there is a setup operation, there is a time duration 1, this carried propagation and sum. Here also carry propagation, sum, carry propagation and sum, carry propagation and sum. When it is Ci is equal to 1, when Ci is equal to 1, when Ci is equal to 1, what happens? There is a skip operation will be there. When Ci is equal to 0, carry propagation operation will be there, and it will be reach a multiplexer. There is a multiplexer here. Here also direction will be there, whether may be a 0 or 1. If 0 means again it will be propagated to a next carry propagation section. Otherwise it will be directly connected to a next multiplexer. So like that, each stage, if there is a carry propagation is 0, what happens? It will be propagated and processed to finally reach this multiplexer. If propagation is equal to 1, what happens? It will be skip the carry propagation block and finally reach this multiplexer. And the sum will be processed by using a summer operation. So it will begin sum 1, sum 2, sum 3 and sum 4. So now carry bypass, suppose if you are using a 16-bit, the number, if you if you find out the delay will be more compared with this ripple carry adder. So that is why by carry bypass adder, what happens? Nothing but 16-bit. So we have to unnecessarily propagate or unnecessarily process the carry operation. So you have to minimize the carry operation by using this carry bypass adder. This carry bypass adder will segregate. If it is 0 means the carry process operation will be happening. Suppose if it is 1 means it will be skipped and processed to next carry propagation. Like that it will be skipped. Finally we get the final carry output, and sum will be processed proportionately. So T adder is equal to T setup plus MT carry plus N_m-1 T bypass plus m-1 T carry plus T sum worst case. So setup time is equal to overhead time to create GP D signals. Okay. So next, carry ripple adder and carry ripple versus carry bypass, both linear. So there is a graph given us drawn between the number of cycles and as well as the time period. So here in case of carry ripple adder, the time taken is more compared with the carry bypass adder. So here it is a 4.8 duration. So here number of cycles, here it may be a time duration will be very high compared to the bypass adder. So what happens generally? So the bypass adder is very suitable because of it is minimizing the delayed time duration. So that is why it is called as a carry ripple versus carry bypass, both still linear. Comparatively, carry bypass adder is very less time duration, and ripple carry adder will be more time duration for processing because the delay will be more. We are familiar about to know in the previous slides. And the carry select adder. So this is somewhat different. So here there is a setup time, whether may be considered as 1 unit, and there is a carry propagation and 1 carry propagation and multiplexer and sum generation. So here there is a setup operation means 1, when carry propagation, when it is 0, carry propagation operation, 1 the carry propagation operation, and here the multiplexer, here it will be select, and finally you are giving the sum operation. So based on the selection of carry, whether we have to process the carry or we have to neglect the carry, based on the selection of logic, whether we have to process or we have to propagate. So and finally given to a multiplexer, the multiplexer will select, and finally we get the carry output and sum generation output. Next, carry select adder. So it is nothing but a 16-bit, consists of, there is a 4, each block consists of setup and carry unit and carry 1 unit and multiplexer and sum generation. And here also second block consists of again some setup box and carry and one carry and multiplexer sum generation. And third block also there is a 8 to 11 setup box, carry and multiplex sum generation. Final block also same as it is. So nothing but 16 bit. So now when you are giving the setup is equal to high, what happens? It will be check whether is there any carry is there. If there is carry is there, what happens? It will be skipped to the next block. Otherwise, if it is carry is equal to 1, so if 0 means it will be processed, 0 means you have to process here, if 1 means shifted here, and the multiplexer will select final output to a next multiplexer. So finally we get some generation. So like that each block will be checking whether carry is 0 or 1. So 0, whether it is 0 means it will be processed to a next carry operation, and finally the carry will be shifted and very fast. Suppose there is no carry means what happens? It will be finally shifted to a 1 carry and it will be set to a multiplexer and directly reach to a sum generation, and in the carry will be transferred to the next block. So like that the carry select adder will be functioning. So it consists of a 16 block. So when you select the carry adder, carry select adder, you have to minimize the time duration as well as delay. So whether carry operation is required or not. If the carry operation is required means you have to process by using a carry as a carry selection. Suppose carry is there means you are going to process it and enter to a next block. If there is carry is not required means directly go through the multiplex section and it will process to the next multiplex section. So like that each block will be verifying whether carry operation is needed or not. If carry operation needed means you have to process, otherwise directly output is reached at the C015. So you have to minimize the time delay. So unwantedly the worst case delay as well as critical path delay you have to minimize by using a carry select order. So next linear carry select order. So it is nothing but a carry select linearly. So here there is the order consists of T setup into empty carry nm T mux plus sum. So here there is a same as it 16 bit carry order. Now here it is a 0 carry and it is 1 carry. Here it is a multiplexer sum generation. So sum generation is 0 0 to 1, 0 to 3, and here it is 4 to 7, here it is 8 to 7, here to 12 to 15. So here first setup is equal to 1. What happens when the carry input is equal to 0? The carry is equal to 0. If there is carry means it will be kind of the next block. Suppose it is 1 means it will be entered to a next carry. Otherwise it will be kind of a multiplex section. Based on the multiplex section whether it is 1 or 0. So 1 or 0, what happens? It will be entered to a next multiplexer. So like that 16 bit will be processed. Finally we are getting a different sum and proportionately we get the carry. The carry is the main process when you are using the adder operations. If there is any delay in the carry operation, the final output will be delayed. That is where we are giving more importance for this carry operation. That is why here carry selector, carry skip order, linear carry select order. So many carry selection order will be there. These orders are skip the process and process operation. Here there is a now here there is a number of processing nothing but 5. Here it will be a 6. Here it will be a 7. So here it will be a 8. So here each operation there is a 5 units. Here also 5 units. Here it is a 5 units. Here it is a 5 units. So when you process this, what happens? There is addition operation. That is why it is 6. Again it is processed. Here it will be 7. Again it will be processed. Here it will be 8. So final operation will be 8 delay units. We will get the final output. Or we have to process this 8. And when here also 9. When you are processing this multiple operation, the delay will be 9 units. So T adder is equal to T setup time. We have set some setup time plus empty carry and n bar m into m bar m into T mux into T plus sum. So next square root carry adder. So here somewhat different about the carry select adder. Here the system consists of first 0 to 1 bit, there is 2 bits, and there is 3 bit, again 4 bit, then 5 bit. So the number of blocks will be gradually increasing number of bits. The first way of consider as 2 bits means second block consists of 3 bits, and third block consists of 4 bit, and 4 bit block consists of 5 bits. So like that, number of bits are gradually increased. When we are gradually increased, what happens? Nothing but there is an operation here, a multiple operation here, it is nothing but 4, and there is a delay operation here, it is 5 units. Here delay units will be 6 units, here delay units will be 7. So we already discussed in the last linear carry adder, what happens? The delay unit will be 9 is coming, but number of delay will be reduces. So delay operation, the number of delays reduces. So when you are reducing such a delay, what happens? We have to minimize the power dissipation as well as the speed will be definitely increasing. That is why square root carry select adder will be minimize the number of delay as well as the delay time as well as the speed will be increases, power dissipation will be reduces. The concept is the first block consists of there is 2 bit, and second block consists of 3 bit, and fourth block consists of 4 bit, fifth class in the 5 bits. So like that, linearly bit is increasing. So that is why T add is equal to T setup plus empty carry plus root of 2n into T max plus T sum. So this is about the square root carry select adder. So now some of the performance graphs are given on the adder delay, adders delay comparison. So now here there is a graph drawn in between these number of cycle as well as the time unit delays. Here there is here it is 20, 40, 60 number of cycles. Here it is nothing but a square root select. Here it is linear select. Here it is a ripple adder. So we are familiar about that ripple adder having more delays compared with the linear select adder or bypass adder. And so when you are comparing about the square root select adder, the delay will be totally reduces. When you are reducing the total delay, what happens? Power dissipation will be reduces, speed will be proportionately increases, and but the number of gates will be, in case the drawback is number of gates will be increases. So this is the main concept. So now the adder delay comparison, when you are comparing this adder delay comparison, what happens? There is a ripple carry adder will be there is a more delay than the square root delay adder. So finally we conclude this the square root delay adder nothing but a very power dissipation as well as delay will be very less based on this performance graph. So now ripple carry adder will get a more delay, and the linear select adder will get the delay less than the ripple carry adder, and bypass select adder has a big comparatively less than the ripple carry adder. The finally there is square root adder select adder will be very less compared with the ripple carry adder. That is why when you are analyzing the adder circuit, we have to use the square root select adder. So that will be minimizing, that is minimizing delay as well as the power dissipation will be less, speed will be proportionately increases. So based on this adder delay comparison graph, we have to select, we have to optimize, we have to get the final idea about the square root delay. Square root select adder is the first one for the adder circuits. So next, look ahead basic adder. So look ahead adder is nothing but this is nothing but, so when you are full adder, what happens? This 4-bit adder, the carry depends upon the previous adder. So when you are depends upon the previous adder, finally carry will be delayed. So when the operation will be sum and carry operation will be getting for a long time. So what happens when you look ahead carry or basic idea? So basic idea behind the look ahead adder or basic idea is nothing but when you are giving the 4-bit adder, when you are connecting a 4-bit adder or 16-bit adder, simultaneously we are getting the carry output. So when you are switch on the look ahead adder or circuits, what happens? When you are giving input, next moment, that is same nanoseconds or milliseconds, the output will be we're getting, because this carry will be shifted or some process. Based on the shifting process, the look at process, we have to minimize. So this is the formula, nothing but C naught k is equal to F into A of k, B of k, C naught into k minus 1, G a k carry generate of kth process, and the P of k propagate, and the C naught k minus 1, nothing but the carry. So this is the input given as A naught, B naught, A1, B1, A n minus 1, B n minus 1, and there is a sum, there is a Ci0 propagate, and propagate means AXR of B, and Ci of 1 here propagate to sum till then till Ci of n minus 1 into Pn minus 1, sum S minus n S n minus 1. So this is the look-ahead topology for look-ahead of equations. So C naught comma expanding look-ahead equations C naught comma k, or we have to G of k Gk plus Pk into G of k minus 1 plus Pk minus 1 C naught into k minus 2. So it is nothing but propagation. So what is nothing but when you are putting k is equal to 1, what happens? G1 plus P1 plus G1 minus 1. So it is nothing but 0. Or we have to consider C of 0, k is equal to consider 0. So what happens? C naught k is equal to 0 means G0 comma 0. Then G is G naught plus P naught into G naught minus 1, and we have to G minus 1 and G naught minus 1 and 1 minus 2. So now it will be gradually increasing. So nothing but here it is the given the formula Gk plus Pk into Gk minus 1 into plus Pk minus 1, P1 into G naught plus P naught Ci into Ci comma 0. So this is the circuit what you drawn. We are familiar about that when both equations, for example P naught and Ci naught will be series, means we have to know that n mass will be connected in series and p mass will be connected in parallel. So based on the logic we have to connect what happens, nothing but p mass will be connected in parallel, and p naught Ci naught nothing but will be connected in series. So here that is why here it will be generate G3, G2, G1, G naught and C naught bar 3, and here it is propagate 0, propagate 1, propagate 2, propagate 3, and Ci of 0, and VDD supply. So we have drawn these equations or by implementing the equations in this diagram. So when you are iterate, first k is equal to 0 and k is equal to 1 and k is equal to 2, k is equal to 3 up to n levels, you have to draw these circuits. Here I think it is a 4 levels you have to draw, up to 4 iteration you have to draw this circuit. The circuit is based on the method of when it is a multiplication there, n mass will be series. If there is a if it is a plus operation, there is a n mass will be connected in parallel. Same it is just opposite of the p mass. When it is a plus operation, a p mass will be connected in series, and dot operation there is a p mass will be parallel. So that is why this will be connected. So the lookup order concept nothing but it will carry very fast, because of when you are giving input at the same time you are getting the carry output as well as some, there is no delay for carry processing. That is why it is called a look-ahead carry order. So look-ahead carry order is nowadays very familiar about that. When you are using a adder circuit, look-ahead adder is implemented in a particular adder circuits. So next look-ahead adder, logarithmic order. So here it is nothing but there is a logarithm, there is a adder a0 a1, and this will be connected to a next adder. So like that, here there is a system called as there is a 4-bit adders, and it will be minimized another 2 set, and then is again minimized, and finally we get the final value. So this also some of the method for minimizing a look-ahead by using a look-ahead adder, finally we get the adder output. So look-ahead adder, logarithmic or adder. So next this is the look-ahead adder equations processed based on the previous equations. C naught is equal to G naught plus P naught into Ci in, and C1 is equal to, this is the general equation, carry out is equal to G naught plus P naught into Ci in, and C1 is equal to G1, generate 1 into, propagate 1 into C naught, and C2 is equal to generate 2 plus propagate 2 into C1, and C3 is equal to generate 3 plus B3 into C3, and so here we have to expand. C naught is equal to G naught plus P naught into C in. When you are applying these equations in a C1, what happens? So C1 is equal to G1 plus P1 into C naught. So we are familiar about what is the value of C naught. We have to directly apply and multiply. So we will get the final equations. So like that, C1 and C2 and C3. So based on this equation, we have to frame C1 value and C2 value and C3 value. So continually can continue building the three hierarchically. So by using this equation, you have to identify simultaneously we are getting output at the carry output at the final step. So that is why it is called as carry lookup trees or carry lookup adder. And multipliers. So here multiplier is nothing but when you are multiply two numbers, whether may be a 4-bit. For example, 4-bit means A1, A0, A1, A2, A3, or B0, B1, B2, B3. So here it is given as Z is equal to X or X into Y. So here summation of K is equal to 0, M plus N minus 1, ZK of K into 2 power K. So here it is summation of Xi into 2I, summation of I is equal to 0 to M minus 1, summation of J is equal to 0 to N minus 1, Yj into 2J. So here I have taken the summation outside. So summation of I is equal to 0 to M minus 1, summation of J is equal to 0, N minus 1, Xi into Yij with 2I plus J. So this is the concept about this. Now this is the binary multiplication when there is a multiplicand and multiplier. So this is the value how much? So one 6-bit multiply with a 4-bit. So this we called as a multiplicand, this we called as multiplier, and when you are multiplying the value, this is nothing but a partial product. So this is the multiplicand, this is the multiplier, and this value we called as the partial product, and this is the result. So when this is the binary multiplication, we are familiar about this. Now this is the array multiplier by 4 cross 4. So this is nothing but there is an input x0 and x1, and there is nothing but y0, x0, x1, x2, x3, and so here nothing but here there is a y0 z1 value. So here when here this is nothing but the AND operation connected to a, so here there is only 2 input, that is why it is nothing but half adder. The extreme will be there is a 2 input, that is why half adder. Remaining will be full adder. So like that, left hand side MSP side there is a half adder, and if there is a 3 input is whenever there is a 3 input is coming, we have to connect full adder, otherwise there is a half adder will be required. So array multiplier 4 cross 4 or 4 by 4. So this is the input x0 and y0. When the x0 and y0, x1 and y0, x2 and y0, x3 and y0, and next second cycle here it is x0 y1, x1 y1, and x2 y1, x3 y1. We contrast z0, and next one half order output equal means z1. Here y2 y2 x1, y2 x1, and y2 x2, y2 x3. So like that it is processing. Wherever there is a input will be 2 means we will be use a half order circuit. Suppose input is 3 means we have to use a full adder circuits. So these are the partial product, and finally we get the output as Z3. We have to get the output as Z1 Z2, Z0, Z1, Z2, Z3, Z4, Z5, Z6, Z7. This is the final answer for the array multiplier. And this is the multiplier when it is a critical m cross n array multiplier with the critical path. So this critical path means here it is a there is a blue color arrow is nothing but a critical path, and a critical path 1, and a red color path nothing but a critical path 2, and a brown color nothing but a critical path 1 and 2. So here there is a formula called m minus 1 plus n minus 2 t carry plus n minus 1 t sum plus n minus 1 the t and. So these are the input, and wherever 2 input is required we have to connect only half adder, and wherever 3 input is required we have to use the full adder circuit. Same circuit is given. And the carry save multiplier. So we already discussed about the carry save adder. When you are, the carry is the main problem for when you are processing addition operations. So whenever the addition operation is coming, the delay will be based on the previous adders. When you are minimizing the particular delay, what happens? The proportionate to the carry will be minimized, carry time duration will be minimized. So carry save multiplier. So this is nothing but a 4 half adders, and here there is a full adders, and there is a again full adders, and there is a full adders. So this is nothing but a more efficient realization can be obtained by noticing the multiplication result not change when the output carry bits are passed diagonally downwards instant to the right. So t multiplication is equal to n minus 1 t carry plus n minus 1 t and plus t merge, but need extra adders or vector machine merging adders that can use the fast carry lookup adder since result come at the same time. Critical path is uniquely defined. So this circuit will minimize the carry save operations. And various tree multiplications is nothing but there is a partial product, and this partial product is again bring it into a group. So first group together and again group together and will merge, and there is a second stage and final stage. Then we will correlate with that. So based on the input selection, there is a 3 input means full adder, 2 input means half adder. So finally it will be segregate pair. Finally you get the answer. So next velocity multiplier. This is the partial product for first stage x3y3, x2y2, x3 x2y3, x2y2, x1y3, x3y1. And x1 y2, x0 y3, x3 y0, and x2 y1, x1 y1, x0 y2, x2 y0, x1 y1, x0 y1, x0 y2. So here there is a different stages. This is nothing but a partial product, and there is a segregation will be there. First stage, second stage, final adder. So when it is a 4-bit, actually there is a half adder in the one pair. This will be connected to a half adder, and in the middle this x1 y2, no, x0 y3 will be connected to a half adder, and there is a 2 output will be coming. This will be connected to the full adder, again full adder, again full adder, again half adder. So after that segregate the output. We will finally get nothing but Z0, Z1, Z2, Z3, Z4, Z5 and Z6. So can use the carry lookup adder for the last stage. Finally you have to use the carry lookup adder for the final stage. You have to minimize the carry delay operations. So same as it is bilateral multiplications based on the n number of the input as well as the proportionally the full adder circuits and carry input circuit is given in the velocity multiplication. So both encoding nothing but there is a eight partial product. So multiply the different inputs, 8 partial product, but 2 all are 0. When add this 0 in the waste time, so instead of multiplying we have to take 1 bar stands for -1. So it is nothing but kind of transformation of both encoding. It reduces number of partial product at the most half of the original multiplier. So each time we have to segregate by using a both encoding process. This encoding is easily incorporated in the overall multiplier design. Shifters. So this is nothing but a binary shifter, whether maybe a left or right, based on the application we have to shift. Parallel shifter, this is the area dominated by, so this is nothing but a parallel shifter, where there is a A0, A1, A2, A3, and output will be P0, P2, B0, P1, B2, B3, and based on the multiplier selection, whether it will be a right shift or maybe a left shift, and shifting process also given here. So finally we will be shifting. And logarithmic shifting, no separate coder decoder is required. Based on the input as well as the selection input, shifting in process input, we have to shift the final process.